Okay, welcome to my second series of lecture on chapter 13, equilibrium. I'm now continuing on from the first part, and I will go straight into the presentation now, and you should be able to follow along the slides with me. All right. So the next topic is on the types of equilibrium. Here we're looking at heterogeneous and homogeneous. So the difference between heterogeneous and homogeneous is that heterogeneous involves several different phases. So you may have different states in the reaction, for example, solid, gas, and liquid, whereas in homogeneous will only be one single phase, and either all in the gaseous state or in the aqueous state or even in the solid state. Now, this is an example of a heterogeneous equilibrium, and this is the decomposition of calcium carbonate to calcium oxide and carbon dioxide. If you look at the states here, calcium carbonate is solid, and calcium oxide is a solid, carbon dioxide is a gas. So there are two states in this reaction. So when we write the equilibrium constant, notice that I'm using the K prime or apparent K. So we'll write it in the same way that we've learned in writing equilibrium constant. Concentration of the products raised to the coefficient. Okay, these are the two products, and then divided by the concentration of the reactants raised to the coefficient. Coefficient here, as you note, are all one. Okay, so why is it K prime or apparent? Now we'll see in here the statement right above here. The position of equilibrium does not depend on the amounts of pure solids and or liquids. So let me highlight that. Let me highlight the pure solids or liquids are not considered to be dependent on the position of equilibrium. So in other words, they are not important for the equilibrium constant variation under equilibrium conditions. So they are given the C1 and C2 value, which basically means constants. They do not change in terms of the value at equilibrium. So now you can put these two C terms together, which are the constants from the solids in the chemical equation, and rewrite it. So this is now what is the true equilibrium constant, K. Notice that is only dependent on the one single entity, and that is carbon dioxide. So it's equal to the carbon dioxide concentration. So another example here, if you have copper sulfate pentahydrate solid, that's a solid, and that decomposes to copper sulfate anhydrous solid and 5 water molecules. You notice there that these are solids and this one is a gas. So if you write the equilibrium constant, the solids are not included, so you will write it as K is equal to concentration of water to the power of 5. Or you can write Kp, because we know that you can all express the Kp for gaseous state reactants or products. So here Kp is equal to the pressure of water, that is water vapor, raised to the power of 5. So the usefulness of equilibrium constant. This is these are the function or the purpose of equilibrium constant. It helps to predict the features of reactions. So you can determine the tendency, that is not speed, of a reaction to occur, which is really a term that we will study more later on. Whether a given set of concentration represent the condition of equilibrium, and then also the equilibrium position that will be achieved from a given set of initial conditions. So we'll be using this as we consider some of the examples in the coming slides. When the value of K is very small, what we're really saying is this: the system at equilibrium will be mostly reactants. In other words, the equilibrium position lies far to the left. That is for very small K value. When we're talking about small K value, you're talking in terms of the order of 10 to the negative 3, for example. Those are very small K values. And then when we are saying that, the reaction really does not occur to any significant extent. Now, the equilibrium constant and time to reach equilibrium are not related. These two are not related. A high K value doesn't mean that the reaction is very fast. That's essentially what it means. So do not associate a high equilibrium constant with a faster rate, because those two are entirely different entities. The equilibrium constant is determined by thermodynamic factors, which is based on energy difference, whereas the rate of reaction really is dependent on this activation energy. So that these energy quantities are not the same. So now let's look at another term that is similar to equilibrium constant K. We call that Q, the reaction quotient. So the reaction quotient essentially is used to determine the direction of movement towards equilibrium when all the initial concentrations are non-zero. So when you're given a set of concentrations, you might wonder, in which direction will this go to reach equilibrium? This is where we use the value of Q. So for example, here, a reaction reactants to form products, we write the expression for K in the same way as we have learned: concentration of the products divided by the concentration of the reactants, right? Raised to their coefficient as shown. Now, all the concentration A, concentration of B and C are the equilibrium concentrations. Now, if you are determining Q, this is what we mean. Q will be the same expression, but concentration are the initial concentrations. So I've designated as a subscript I, meaning initial. So Q will be equal to initial concentration of C divided by the initial concentration of A multiplied by the initial concentration of B, of course raised to their coefficients. So K is based on the equilibrium, while Q is based on initial concentration. Now, in the rest of the slide, you will notice that this term here is not, subscript not. That is a subscript used by the text. I'm just emphasizing the initial by putting in I here, but the text uses not. So this is essentially what it means. If you have the Q value less than K, that means the equilibrium will shift to the right. And if the Q value is greater than K, the equilibrium will shift to the left. And if Q is equal to K, the system is at equilibrium. Now let's consider this example. For the synthesis of ammonia, at 500 degrees Celsius, the equilibrium constant is 6 times 10 to the power of minus 2. Predict the direction in which the system will shift to reach equilibrium. So you're given the initial conditions here. Now you see the subscript used by the text. All right. So these are the initial concentrations of ammonia, nitrogen, and hydrogen. So what do we need to do? We evaluate Q. So Q comes from the Haber process, that is the reaction we've looked at previously. This is the products or product, and that's coefficient, and then these are the reactants raised to their coefficient. Notice that these are initial concentrations, so I'll substitute it in the initial concentrations. I get the value. Now you see that this value 1.3 times 10 to the power 7 will be compared to the value of K. So this is the Q based on the initial. You compare that with the K. So Q is much greater. Much greater. So what does that mean? That means according to this system, look at this. According to this system, with this concentration, when you start the reaction, it will shift to the left. Means these two are going to be the favored products. So this is what will happen, or what is predicted from the value of Q. That the reaction is going to start from the right and move to the left. So in other words, more of these two will be formed, and some of this will be used up. Now we will go into some of the mathematical approaches. In other words, some of the problems that we apply the equilibrium system in, and then work out values of the quantities at equilibrium. So you may be given a set of initial conditions and find the equilibrium concentrations, or you're going to be using the equilibrium concentration and find the set of initial conditions. These are the way we will look at some of these problems. Let's consider one simple one where you have only one reactant and one product. So this is the reaction of dinitrogen tetroxide to form nitrogen dioxide. So this is a homogeneous equilibrium, that is the balanced equation. Now, this is a given set of conditions. Say, for example, the Kp value is given 0.133, and then you have the at equilibrium, the pressure of N2O4 was 2.71 atmosphere. Calculate the equilibrium pressure of hydrogen dioxide. So notice that you're given the Kp, and you're given the pressure of the reactant. So here you need to find out the pressure of the product. That's a very simple setup. If you look at the equilibrium constant equation. So here you will see Kp is equal to pressure of the product, which is nitrogen dioxide squared, over pressure of dinitrogen tetroxide. And that should be equal to this value here, which is given, 0.133. So what else is given? We are also given this. So we'll substitute that in the next slide, so in the next point. So here it is. The pressure of N2O4 is 2.71, and this is the equilibrium constant under pressure at using pressure, and then you can solve the pressure of hydrogen dioxide. So notice that this is a squared function, so you need to find the square root of that. So pressure of nitrogen dioxide will be the square root of 0.360, and that gives us the answer. So pressure is 0.6 atmosphere. That's the unit of this calculation. Now let's look at another example. This one, we're going to look at this chemical reaction. Again, in the gas phase, all of them in the homogeneous system. Phosphorus pentachloride to give you phosphor trichloride and chlorine gas. Now that's a balanced equation, as you can see. And you can write the equilibrium constant, K, which is the concentration of the products divided by the concentration of this, or pressure of the products divided by the pressure of the reactant. Now, let's look at the given conditions. So here you're given the volume, 1 liter, and contained initially 0.298 moles of PCl3 and 8.70 times 10 to the negative 3 mole of PCl5. So you're given initial quantity of these two. Okay, this one here, it is 0. So this initial quantity of this two species, and this one, there is none at the beginning. It says calculate the equilibrium concentration of all species and the value of K. So how do we approach this? That is the chemical equation, and let's look at the equilibrium expression. So that is the equilibrium expression. Now to find the value of K, we calculate the equilibrium we need to calculate the equilibrium concentrations of all species and substitute the derived quantities into the equilibrium expression. So we'll need to come up with a mathematical representation for this in order to solve the problem. So this is where it gets a little bit complex, because there is an unknown quantity that we'll need to take into account. So we'll see how we'll set this up. So let's just look at the initial concentrations. So here we have chlorine 0 and phosphorus trichloride. Now we have to convert these to concentration, so mole divided by the volume, and the volume is a liter, so that makes it easy because it's only divided by 1. So you get, now you have the number of, the molarities of the initial concentrations of the two species here. So now we're going to set up. We know this, the equilibrium amount of Cl2 is given in the equation. So we are going to use this argument, the mole ratio. That is, if you have a certain amount of the reactant to be consumed, it'll form a proportionate amount of these products, as we've learned from stoichiometry. So an example is stated here. Because it is a 1 to 1 to 1 mole ratio, so we can say this: if minus 1 mole, if 1 mole of this is consumed, that means 1 mole of that will be formed, 1 mole of this will be formed. Notice that if it's 1 mole consumed or taken away, here you expect it to increase by 1 mole, and this one also by 1 mole. So this is a setup. Minus 1 mole, you expect plus 1 mole for this, and plus 1 mole for chlorine. So let's just apply the quantity that is given here. 2 times 10 to the power minus 3. So 2 times 10 to the power minus 3. So this will be minus 2 to the negative 3. This will be plus 2 to the negative 3 plus 2 to the negative 3. And at equilibrium, notice now, we are setting up the expression for the equilibrium. So here it'll be 0, because it started with initial 0 plus 2 to the 3. Here it'll be 0.298 plus 2 to the 3. Here it'll be 8.70 by 10 to the 3 minus, so you notice that, minus 2 to the 3. And so apply that. So we can now set it up. Evaluate these values. So this becomes 2 to the 10 to the 3 minus 3. Here is 0.3, and this one is 6.7 times 10 to the minus 3. So substitute that into the K expression. We will get the value of K, which is 8.96 to the times 10 to the negative 2. So simple substitution of the values that we have evaluated. So we get now the value of the equilibrium constant. Okay. Now let's look at another example for calculating equilibrium concentration. So here we're looking at the formation of hydrogen fluoride from hydrogen and fluorine, and you're given the equilibrium constant as 1.15 times 10 to the power of 2 at a particular temperature. So then you have the quantities, 3 moles of each component were added to a 1.5 liter flask. So in other words, these are the starting condition or initial. So 3 moles of each, that is the reactant and the products, were all mixed in this flask. So we write the chemical equation. So that's the equation. And notice the stoichiometry there. Now we find the equilibrium expression. K is this. So 1.15 times 10 to the power of 2 is equal to concentration of HF squared over the concentration, or the product of these two concentrations. Now, the initial concentrations are 3 moles of each of this. That was mixed into a 1.5 liter. So, in other words, these are all the concentration. They were at the start. So let's determine the value of Q. Why do we calculate the value of Q? The reason is that we want to know the direction this reaction is going to go. So we calculate the value of Q based on the initial concentration. So here is 2, 2, 2. Okay, this one is squared. You get 1. Since Q is much less than K, so you compare Q to K. K is this value here. This is K. Is 115, yes, 115, compared to this value here is only 1. So Q is much less than K. So what does that mean? The system must shift to the right. So this is very important. For Q less than K, the system will shift to the right to reach equilibrium. So to determine the change in the concentration necessary, we define the change needed in terms of X. So watch this X term here. We note the direction and we will follow that. So here, the stoichiometry of the reaction shows that X mole per liter of F2 will be consumed and 2X mole of HF will be formed. So here's the stoichiometry. X mole, if this is consumed, that will be formed 2x according to the stoichiometry. So the setup that we will have is this. For the hydrogen, you start with 2 molar, and then the change will be minus x. Fluorine will be 2 molar starting, change will be minus x. And then the product, HF, you start with 2 molar, but the change will be plus 2x. So here are the concentrations that you expect at equilibrium. 2 minus x, 2 minus x, and 2 plus 2x. So this is very, very important because that will lead you to a setup that you can solve mathematically. So let's see that. The concentration can be expressed in a shorthand table as follows. And this is a very important table that we will be using in most of the problems that we will solve. Notice that the balanced equation is up here, and these are the initial quantity in concentration, mole per liter. Those are the initial, and the change minus x plus 2x, and now the equilibrium. So you basically take initial minus x, and then initial plus 2x. So this table here is called, in short, ICE table. I meaning the initial, C the change, and E the equilibrium. So now we can set this up because this can be expressed into the K expression. So let's look at that. Notice that. So K is 115. So that'll be equal to the equilibrium constant concentrations term. And substitute in the values. So this is 2 plus 2x squared. And this one is 2 minus x, 2 minus x. So you can square that. Now, when you have this sort of square function, the right-hand side of this equation is a perfect square. So taking the square root of both sides will lead you to a very quick solution for x. So square root on both sides and solve for x. X is 1.528. So that is the change in the concentration, right? That's change in the change in the quantity or change in the amount. So now we need to find the actual amount by substituting. So that's what we will do. So the concentration of H2 and F2 is 2 minus x. So that will be 2 minus 1 point, what is x? 1.528, and that gives us this value, 0.472. And the product will be 2 plus 2x, so it'll be 5.056. So here we have the concentrations of all species at equilibrium. How did we get it? We have to apply the stoichiometry and the ICE table. So remember that. That's a very important step in the calculation of this. Now let's go on to the summary of how we solve this sort of equilibrium conditions or equilibrium problems. First, we need to have a balanced equation. And then from the balanced equation, we write the K expression, that is the equilibrium. And from that, from the given initial conditions, you can calculate Q. So that Q will tell the direction in which the system will go or the reaction will go, and then define the change. Because when you know where the direction is, the change is critical because you'll know which one is consumed and which one will be produced, so, or formed. So in other words, it'll tell you the direction and also the right amount, quantities, one that will be negative and the one that will be positive. So then substitute the equilibrium concentration into the expression and then solve. Now, one thing about solving this, you will realize that this gets into some polynomial mathematical function. So watch that very carefully, because we will need to solve some of this and know how to solve it. And we'll start with some simple ones, but expect some complex one as we go. So let's look at this particular example, and then we should try and wrap it up with this second set of slides. So let's look at this one. Gaseous hydrogen iodide is synthesized from hydrogen and iodine vapor, and the temperature at a temperature where the equilibrium constant is, well, this number is 100, 1.00 times 10 to the power of 2. So suppose that you have 5.0 times 10 to the negative 1 atmosphere of so you have these pressures of the different species that you started off with. So these are the initial conditions. You have 0.5 atmosphere, 0.01 atmosphere, and 0.005 atmosphere of I2. So these are all mixed in a 5-liter container. Question: calculate the equilibrium pressures of all the species. All right. So let's bring in the equation. That's the equation. H2 plus I2 giving you HI. That is the balanced. And you see the stoichiometry from there. 1 to 1 to 2. So the equilibrium term for pressure is pressure of products, this one, squared divided by the pressure of the reactants. So that gives the value that is provided, 1.00 times 10 to the 2, which is 100. Now let's set in the initial condition that you see here. The initial pressures are provided, so these are the pressures for HI, H2, and I2. Please note that this not here should be subscript, so it's not really giving the right position, so it should be all below. Okay, let's move on. So let's calculate the value of Q. You find out the value of Q. We find out it's 5 times 10 to the power of 3, which is 5,000. So this is 5 to the 3, and we can compare that with the K that is given. Okay, compare that. You'll find that Q is greater than K. That means the system will shift to the left. That's very important. When you see that it is the reverse of what we are looking at, you have to be careful so that you will set it up in the right format, in the right equilibrium expression. So now we use the pressures for the gas phase system at constant temperature and volume. Now I just highlight this. If you are looking at the gas in terms of number of moles, the pressure of gas is essentially proportional to the number of moles. So here is from the ideal gas equation. So when we are talking about pressure, that is essentially directly proportional to the mole. And you will see that this is essentially looking at ideal gas equation. Okay, so what we can do now is set up the ICE table. So watch this table. Initial, change, equilibrium. So start with the initial. This is the initial pressures, which we now consider to be proportional to the mole quantity. So these are for the two reactants, and that is the product. So now the change. What's the change here? In which direction is this reaction is going? There. How did we get this? We got it from the value of Q. So that means this will decrease, that's why it's a negative here, and these two are going to increase. Very important. So this will be, according to the stoichiometry, minus 2x plus x plus x. So now equilibrium will essentially be initial minus 2x, initial plus x, initial plus x. Once we have that, we can then bring that into the expression for Kp. So notice that expression for Kp is concentration of Pi squared, P of Hi squared over pressure of H2 and I2. So we substitute in these numbers here, these values from the equilibrium expression. And you will notice that this is going to be, I mean, it's looking complex in terms of what we are solving. But what you will see in here, essentially, this is just a quadratic function. So you will get a quadratic equation in the form of ax squared plus bx plus c, and then solving that. So here's the value of a simplified, and that's the value of b, and that's the value of c. Now, recall, when you solve quadratic functions, you can solve it by rearranging to equal 0 and use the quadratic formula. I'll show you the formula, and that's the formula for quadratic function. X is equal to minus b plus or minus b squared minus 4ac, where you have this a, b, and c form. So if you look at this equation, the solution for that is 3.55 times 10 to the power of minus 2. So now we have the x, which is the change that we calculated, and from the change we can find the equilibrium concentration or equilibrium quantities. So in this case will be pressure. So now we can subtract 2x from the product. That'll give us the quantity of the product, and this one, the two reactants, you plus x, I'll add x to that. So here you'll get it, and likewise you add the quantity x, which is 3.55 times 10 to the negative 2. So these are now the equilibrium quantities, in this case pressure. So let's do that, and we can evaluate and find the value of K. So if you calculate the substitute in the pressures at equilibrium, you come to 99.99, which is pretty much similar, it's almost the same as the K value that we were given. So calculations is correct. Okay, I'll finish off with this example in this slide, and that is the now what sort of calculation we carry out for very small k. Now we're looking at very small k, and this is an example like 1.6 times 10 to the power minus 5. That's a very small number. So if you have a small equilibrium constant, how do we deal with that in the calculation? We're going to follow exactly the same step, but watch one of the important steps that we're going to carry out. So here you have the equation, NaCl, to give you NO and Cl2. That's the coefficients, or the stoichiometry, 2 to 2 to 1. Now you have this. The following step: determine the equilibrium concentration of NaCl, NO, and Cl2 when 1 mole of NaCl is placed in a 2-liter flask. So here you start with the initial quantity of this, 0 of these two. So when you have this scenario, this is how you work through it. When you start with the reactant and none of the product, there is only one direction this will go, to the right. So you don't need to calculate the value of Q. So the equilibrium expression is this, and the initial conditions are, notice that, you're only given the reactant, 0 of the products. So, since there are no products initially, the system will move to the right to reach equilibrium. So we can now set up the ICE table. So this one will be 2x, this one will be 2x, and this one will be x. But let's try and put in the sign, because we should know which one is consumed. This one will be negative, this one will be positive, this one will be positive. Okay, see the ICE table. That's the balanced equation, initial quantities, and now you have the change, minus 2x, because this is consumed, plus 2x, plus x. So now the equilibrium concentration will be initial minus this, initial plus this. So you'll have 0.50 minus 2x, 2x, and x. So now we can substitute in to the equilibrium constant, and we see that that is equal to NO squared Cl2 over NOCl squared. So substitute in this variables, you'll have 2x squared times x divided by 0.5 minus 2x squared. All right. Now, this is a very important step. In this situation, K is so small that the system will not proceed far to the right to reach equilibrium. So what do? X represents a relatively small number. So when x is small, we can make this approximation. So this is the approximation. What do? 0.5 minus 2x is approximately 0.5. Because we're assuming that x is so small that there's hardly any change in here. We can do that because K is very small. So now let's rewrite the equation using this approximation. 2x squared times x over 0.5 minus 2x. This will be reduced to 0.5. This 2 remains. We don't use that out here. So this becomes 0.5, and this is 2x squared times x. So it becomes 4x cubed over 0.5 squared. And that's an easy function to solve. So now we can simplify this. X cubed divided by 4, that divided by 4, that gives you 1 to the minus 6, and then cube root of that number will give us 1 times 10 to the minus 2. So now we have the value of x by using approximation. When we use approximation, we'll try and see how valid this is, so we can test it. So if x is 1 times 10 to the negative 2, then 0.5 by minus 2x will equal 0.48. So in other words, 0.48 and 0.5 are not any far different. Okay, you'll see that it is a difference of 0.02, which is not highly significant for very, very small change. Okay, so now use the approximate values of x, the approximate value of x, to calculate equilibrium concentration. So let's do that. So this is the approximation we did. That will be the concentration of NOCl. NO will be this number that we have calculated, and likewise of chlorine is that from the calculation. So what do we get? When we substitute in these values, we get 1.6 times 10 to the power minus 5. Since the given k value is the same, that means our approximation was very good. Okay. So that sort of brings me to the conclusion of this set of for this part 2 of the talk or the lecture. So let me just summarize. We've covered the heterogeneous aspect of equilibrium, and in heterogeneous, when we cover pure solids and pure liquids, they are not part of the equilibrium constant. They are considered constant, so they do not appear in the equilibrium expression. Now you see that reaction quotient deals with the concentrations of system at initial condition, so that can be used to provide the direction where the reaction will proceed in order to reach equilibrium. And given any set of initial conditions or amount, we can set an ICE table using the mole ratio to solve the equilibrium concentration. So that brings to the end the part 2 of this topic, chemical equilibrium, and thank you for listening.